You're listening to DTFHN for July 14th, 2026. I'm your open-sourced against medical advice host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass pedantry occasionally produces insight. Today's a day for gates left open and ladders left standing. Let's get into it. I've spent enough time building systems with resource constraints to know that the hardest engineering problem is rarely the first extraction. It's the second one. Getting lithium out of the ground is chemistry. Getting lithium back out of a spent battery cathode, at purity levels high enough to feed back into manufacturing, that's where the craft lives. Japan's latest recycling advance hits 90% lithium recovery from used EV batteries. And the chemical insight is genuinely elegant. Traditional hydrometallurgical recycling uses sodium hydroxide to process black mass. That's the shredded, mixed powder you get after dismantling a battery pack. The problem is sodium contaminates the lithium stream, making downstream purification expensive and energy-intensive. What this team did was substitute recovered lithium hydroxide for the sodium hydroxide. You're using the target element as your own reagent. The lithium stays in family through the entire process. So your output purity goes up and your separation costs go down. They're also reporting a 40% reduction in carbon emissions compared to conventional methods, which tracks. Fewer purification stages means less energy. Now, let me play devil's advocate, because the comments on this story are doing important work. Multiple readers pointed out that 90% lithium recovery is not actually unprecedented. Mercedes opened a battery recycling plant in 2024, claiming 96% recovery across the whole cell. Companies like Li-Cycle, Redwood Materials, and several Chinese firms are already operating at commercial scale with comparable numbers. The article names no specific research institution, no lead scientist, no published paper. That's a red flag for anyone trying to evaluate the actual novelty here. But here's why I think the story still matters. And it's not the number, it's the geopolitical architecture. Japan imports nearly all of its battery minerals. In 2010, China cut off rare earth exports to Japan over a territorial dispute. And that single event rewired Japan's entire materials strategy. This isn't a country optimizing recycling because it's trendy. It's building domestic supply chain resilience because it has lived the consequences of dependency. The fact that only 14% of used lithium-ion batteries in Japan currently enter recycling streams tells you the bottleneck isn't chemistry. It's collection infrastructure. It's logistics. It's the unsexy plumbing that determines whether a lab breakthrough becomes an industrial reality. The deeper engineering truth here is that battery recycling is a solved problem at the chemistry level. What remains unsolved is making it economically competitive with virgin mining at scale. Every facility that ships, every process that shaves cost per kilogram moves that threshold. Japan's target of processing tens of thousands of tons annually by 2035 is the part worth watching. The recovery percentage is a headline. The tonnage is the revolution. So we're reclaiming the atoms. But what about reclaiming the compute? What happens when CUDA stops being NVIDIA's moat? Let me make the case for NVIDIA's CUDA lock-in. Seriously, They spent 2 decades building the most robust GPU programming ecosystem on the planet. Billions in R&D, thousands of engineer years of documentation, tooling, debugging infrastructure. They earned that moat. Why should anyone get to waltz in and run CUDA on competing hardware? That's not innovation. That's free riding. And you know what? That argument is airtight right up until you remember how C++ works. Nobody expects a performance penalty when you compile C++ for an ARM chip instead of an x86 chip. The compiler handles it. That's the entire point of a compiler. Spectral Compute looked at GPUs and asked the obvious question. Why doesn't this work the same way? Scale is their answer. A clean room reimplementation using Clang and LLM. The same compiler infrastructure that already lets you target basically any CPU architecture on Earth. Applied to GPUs. Drop it in where NBCC sits, recompile, and your CUDA code runs on AMD hardware. Their published benchmarks show nearly 6 times the performance of AMD's own HIPified translation tool. 6 times. On AMD's own GPUs. The comedy here is exquisite. NVIDIA built CUDA so well, made it so ubiquitous. 80% of HPC code in the wild. That they accidentally created the strongest possible argument for making it portable. They built the standard. Now the standard wants to leave home. And the existing alternatives each fail in instructive ways. HIPify ignores PTX, the assembly-level instructions where real optimization lives. SYclamatic migrates 90% of your code and leaves the hardest 10% as homework. CUDA intercepts compiled binaries, which is clever but slow. Each one treats CUDA portability as a translation problem. Spectral treats it as a compiler problem. That distinction matters. The bootstrapism angle writes itself. CUDA knowledge is arguably the most valuable technical skill in AI and HPC right now. Millions of developers, decades of code bases, all of it chained to one company's hardware pricing. Scale doesn't replace that knowledge. It makes it portable. The ladder stays where it is. More people get to climb it. One Hacker News commenter nailed the usual trajectory. Bull's launch works for 3 operations, then the Discord server where the last messages, any updates. From 2 years ago. Fair. The graveyard of CUDA alternatives is well populated, but Spectral's been at this since 2018, has $6 million in funding, and their approach. Treating GPU compilation the way we already treat CPU compilation isn't novel, it's overdue. So open tools let more people climb the ladder. But what happens when the energy powering those tools becomes free? 24 kilowatt hours. That's the daily cap Australia's government added to its free electricity scheme after public consultation. It's also, according to the Australian energy regulator's own benchmarks, roughly what an entire 5-person household uses in a day. They set the ceiling at the point where almost nobody hits it, which tells you this isn't really a cap. It's a permission structure. Starting July 1st, energy retailers in New South Wales, South Australia, and Southeast Queensland must offer households 3 hours of free electricity during peak solar hours. No panels required. No homeownership required. Smart meter, opt-in, done. The mechanism is worth understanding because it's elegant in the way that good plumbing is elegant. Australia has 4.3 million rooftop solar installations. Every clear midday, they flood the grid with more electricity than the market can absorb. Wholesale prices go negative. Retailers have been paying to offload power that consumers never benefit from. The solar sharer offer just connects the pipe. Surplus energy that was being wasted or sold at a loss. now flows to households at zero cost during the hours when the grid is drowning in it. This is orcharding. Specifically, it's what happens when a fruit tree produces more than a family can eat. You have two choices. You can let the excess rot on the ground while maintaining that fruit is a scarce commodity, or you can open the gate and let the neighbors pick. Australia chose to open the gate. The fruit was already falling. The comments on this one are sharp. Several people immediately asked the obvious follow-up. If midday price swings are this extreme, why aren't grid-scale batteries printing money? The rough math someone ran suggests 20 kilowatt-hours of arbitrage per cycle makes battery installations highly economical. Others pointed to desalination and carbon capture as industrial processes you could schedule around free power windows. These aren't hypotheticals. These are engineering responses to a price signal that now exists in law. Victoria is under consultation for an October expansion. Other states expected by 2027. The trajectory here is clear. What's worth noticing is the architecture of this policy. It doesn't subsidize, it doesn't create a new market. It takes energy that already exists, that the grid already produces, and removes the artificial barrier between surplus and consumer. The scarcity was never in the electrons. It was in the billing software. 4.3 million solar installations built by individual households, generating collective surplus, now shared as a public benefit. That's the bootstrap. People built the infrastructure. The policy just stopped pretending it wasn't there. So, what happens when you apply that same philosophy? Pause. Make the invisible visible. Pause to your own development history. 18 years. That's roughly how long Git has shipped without a sane way to fix a typo in a commit 3 deep in your stack without risking a half-broken tree. 18 years of interactive rebase fear, of developers memorizing incantations like fix up auto squash update refs, and hoping nothing explodes. And now, quietly, across 2 releases that most people apparently slept through, Git just solved it. The command is git history. It landed in Git 254 and 255, April and June of this year. And it does something that sounds almost too simple to be newsworthy. You stage a fix. You point it at an old commit, and it folds the change in and rebases everything downstream. Every branch. Atomically, if anything would conflict, it refuses the operation entirely. Your tree never enters a broken state. That's the engineering detail worth admiring here. The atomicity guarantee. Interactive rebase is powerful, but it's essentially a multi-step mutation of your commit graph, and if step 4 of 7 hits a conflict, you're stranded in rebase limbo. Grepping stacked overflow for the abort sequence. Git history treats the entire rewrite as a transaction. It either completes cleanly or it doesn't happen. And the question nobody seems to be asking: why did this take so long? Jaja's the Jujutsu version control system has been getting breathless coverage for solving exactly these problems. Parallel branches, easy history rewriting, automatic rebasing, and it does solve them well, but Git history delivers a meaningful subset of those benefits inside the tool that 7 billion repositories already use. No new mental model, no migration, no evangelism required. The 3 subcommands map to what developers actually do when they're iterating. Fix up amends an old commit with staged changes. Reword edits a commit message anywhere in the stack. Split breaks one commit into 2. All three auto-rebase everything downstream and move branch pointers. All three are atomic. There's a limitation worth naming. Git history can't handle merge commits, and it won't push through conflicts. JJ treats conflicts as first-class objects you can resolve later. The Git docs explicitly acknowledge this gap and leave the door open for first-class conflicts in the future. But here's what matters. This isn't a third-party tool. This isn't a wrapper script someone posted in a gist. This is core Git, maintained by the same community that maintains the infrastructure half the world's software runs on. Open source iterating on itself, absorbing good ideas from its own ecosystem, shipping them where everyone can reach them without switching anything. The best tools don't ask you to change your life. They just quietly get better. What happens when you map something even more intricate than a code base? Story 5. Indian scientists produced the most detailed 3D atlas of the human brainstem. One of the top voted comments on this story is someone reacting to the fact that the researchers made the atlas freely available online. And, I'm quoting here, "Duck yes. Finally someone not gatekeeping life-saving technologies so they can make a shit ton of money out of it. That's raw, and it's earned." A team at the National Brain Research Center in India has produced the most detailed three-dimensional atlas of the human brainstem ever constructed. We're talking about a region roughly the size of your thumb that controls breathing, heartbeat, consciousness. The stuff you absolutely cannot afford to get wrong during surgery. And until now, neurosurgeons navigating it were working with what amounts to two-dimensional slices and educated guesswork. The historical parallel that comes to mind is the Human Genome Project. Remember how that played out? Craig Venter's Fellera Genomics was racing to patent the genome. Lock it behind licensing fees. Turn the blueprint of human biology into a revenue stream. The public consortium said no. This belongs to everyone. They won. And the entire field of genomics exploded precisely because the data was open. Every CRISPR therapy, every mRNA vaccine, every genetic diagnostic traces back to that decision to publish freely. Now here's a team in Manindzer, India, doing the same thing for neuroanatomy. They've mapped structures in the brainstem that weren't even clearly documented before. Features that could help doctors identify brain tissue that's damaged but salvageable after a stroke. The difference between recovery and permanent disability, sitting in an atlas anyone can access. And the slightly bemused part of my brain notes that someone in the comments felt compelled to ask whether this is really just a reference built from a small number of individuals, which, yes, that's how atlases work. That's how Gray's Anatomy worked in 1858. You build the reference, then the field iterates on it. The point isn't that it's a diagnostic tool for your specific brain. The point is that neurosurgeons now have a three-dimensional map where they used to have a rough sketch. You can pull up the atlas yourself. Anchor.humanbrain.in. Spin the brainstem around in your browser. The tools exist. The data is open. A research team in India just handed the entire field of neurosurgery a better map. And they didn't charge admission. This is how open science is supposed to work. Most of the time it doesn't. Today, it did. Moving on. Graph databases solve a specific problem that relational databases handle poorly, when your data is defined by relationship. Who connects to whom? What depends on what? Which issue blocks which other issue? A traditional SQL database forces you into joins. Every join is a runtime computation. The more relationships you traverse, the worse it scales. Graph databases flip this. They store relationships as direct pointers. Traversing a link is AMR O1. Constant time. It doesn't matter if your database has 10,000 nodes or 10 million. Following a connection costs the same. JetBrains has been building issue trackers for over 2 decades. UTrack is one of the most widely used project management tools in the industry. And the entire time, they've been running it on top of a graph database they built internally. That database is now open source. It's called YouTrackDB. The technical foundation here is worth understanding. YouTrackDB implements object-oriented modeling at the database level. Inheritance, polymorphism, the full hierarchy. It supports Tinkerpop and Gremlin out of the box, with GQL support in progress. Snapshot isolation is the default transaction model, which means every transaction sees a consistent view of the database from the moment it started, and it ships as a single shaded Uber jar that relocates all its dependencies so it won't conflict with whatever else you're running on the JVM. One of the comments pointed out something genuinely surprising. It's written in Java, not Kotlin. JetBrains literally created Kotlin. But production databases are conservative beasts. You optimize for stability and ecosystem depth, not language elegance. That's a pragmatic choice that tells you something about how seriously they treat this code base. Another commenter dug into the repository and found 25 Claude agent definitions in the .claude directory, 10 of them dedicated to different dimensions of code review. JetBrains is using AI-assisted development workflows on their own database engine. That's not a press release. That's the actual commit history. The question people could be asking is whether graph databases are worth the complexity. The answer depends entirely on your data shape. If your queries are fundamentally about traversing relationship, and issue tracking is exactly that, then paying the join tax on every query is the wrong trade-off. JetBrains proved this works at scale internally. Now anyone can run it, embed it, extend it. The code is on GitHub, the Docker image is public. The tools are available. That's the whole point. We talked about removing gatekeepers from infrastructure. Now let's do the same thing to app development. In 1984, Apple ran the most famous ad in computing history to sell you a graphical interface. The whole pitch was that you'd never have to type commands again. 42 years later, the most productive way to build software for that same platform is to close the graphical interface and type commands. There's a beautiful irony buried in Scott Wilsey's walkthrough of headless Mac and iOS development. Every tool you need already exists inside Xcode.app. Xcode Build, Notary Tool, Stapler, Divs, Sadle. They're all there, sitting in the application bundle, waiting to be called from a terminal. The GUI is a wrapper. It always was. Let's follow Apple's own design logic to its conclusion. Xcode is supposed to be the integrated development environment. Integrated means everything in one place. But integration has a cost. The project file, that .xcode prod bundle, is actually a folder full of XML that Xcode rewrites constantly. Every file reference, every build setting, every team member's change creates merge conflicts in Git. The tool designed to simplify your workflow becomes the primary source of workflow friction. Xcode Gen solves this with a single YAML file. Describe your project declaratively. Regenerate the Xcode project on every build. Commit the YAML. Git ignore the rest. This is the Unix philosophy reasserting itself inside Apple's walled garden. Small tools, plain text, composable pipeline. What Wilsey documents is a one-time setup. Sign into your Apple ID. Create your developer ID certificate. Store a notarization password in the keychain. After that, a single shell script runs the entire release chain. Archive, sign, notarize, staple, install. The signing key lives in your keychain. No secrets in the repo, no GUI required. The comment surfaced something worth noting. Someone points to Xtool. an open-source project that lets you build and test iOS apps on Linux. No Mac required at all. The proprietary toolchain is being systematically unbundled by people who want to build where they are, not where Apple says they should be. This is builder culture at its finest. The craft here isn't in fighting the IDE. It's in recognizing that the IDE was never the tool. The compiler was, the linker was, the code signing infrastructure was. Xcode is a front porch on a factory. Some people like sitting on the porch. Others walk straight to the floor. Remember that textbook liberation we talked about earlier? Here's another one hitting different. Story 8. Fundamentals of Wireless Communication. How long does knowledge stay fundamental? That's the question buried in this story. A textbook on wireless communication, published in 2005, written by David Say and Pramod Viswanath at Stanford and Illinois, is sitting on a university webpage right now. Full PDF, there was exercises included. Covering the theory that makes your phone work. Someone in the comments asks the obvious question, how relevant is this in 2026? Run this forward. The book covers multiple input, multiple output, which is the reason your Wi-Fi router has those little antennas sticking out like a startled insect. It covers OFDM, the modulation scheme underneath every 5G signal hitting your phone right now. It covers capacity theory, diversity multiplexing trade-offs, space-time coding. These aren't historical curiosities. They're the load-bearing walls of modern wireless. Every engineer at Qualcomm designing the modem in your pocket learned this math somewhere, and a disturbing number of them learned it from this exact book. The comedy is in the timestamp. 2005. YouTube launched that year. The iPhone didn't exist yet. And here's this textbook laying out the theoretical framework for a wireless world that wouldn't fully arrive for another decade. The math was ready. The silicon caught up later. One commenter notes the book glosses over OFDM in a single short chapter. Fair, but that's actually the tell. OFDM is an implementation detail. The book is teaching you to think about channels, about what information theory permits, through a fading, noisy, shared medium. That thinking doesn't expire. Shannon's channel capacity theorem is from 1948, and it's still the ceiling everyone's building toward. And the book is just there, on a Stanford webpage. PDF files you can open in any reader. No paywall, no platform, no login. Cambridge University Press holds the copyright, and yet the authors put the entire thing online. 50+ universities teach from it worldwide. This is what knowledge distribution looks like when someone decides the point is the teaching, not the transaction. The fundamentals don't age. The textbook aged exactly as well as the math it contains, which is to say, it hasn't aged at all. The protocols built on top of it will churn through versions and standards, bodies and marketing names. The theory underneath just sits there, free, waiting for whoever needs it next. Moving on. Every system I've built eventually needed a display, a status panel, a dashboard, a single number someone could glance at from across the room. The engineering challenge is never the rendering. It's the mounting, the power, the question of what happens when you need to change what it shows. That last part is where architecture matters. This project is a circular LCD wall clock. 7-inch round display, 1080 by 1080 pixels. driven by a Raspberry Pi over HDMI. The clock faces run in a web browser. Firefox, full screen, rendering whatever HTML and CSS and JavaScript you pointed at. The entire clock engine is a URL. I want to be precise about what that means. The display hardware speaks standard HDMI. The compute is a general-purpose Linux board. The interface layer is a web browser. Every component in this stack is substitutable. You can swap the Pi for any single board computer. You can swap the browser for a native renderer. You can swap the clock face by changing a bookmark. The person who built this isn't locked into anything, and neither is anyone who copies the design. The comments are revealing. Multiple people point out that running a full browser to display a clock is computationally wasteful. They're correct. A microcontroller drawing directly to the frame buffer would use a fraction of the power. But that critique mistakes efficiency for the objective function. The objective function here is hackability. A browser means anyone who can write a web page can design a clock face. That's a dramatically larger population than people who can write bare metal graphics code for embedded displays. This is a pattern worth naming. When you choose the less efficient but more accessible architecture, you're trading compute for participation. The Raspberry Pi Foundation has been running this trade for over a decade, and the results speak for themselves. Millions of people learned to build things because someone decided that a $40 Linux board with standard connectors was more important than an optimized appliance. The clock works. It tells time. It also teaches anyone who encounters it that a display is just a surface. A computer is just a driver. And the interesting part, the face you design, the information you choose to show, belongs to whoever holds a keyboard. We talked earlier about tools that get out of your way. Story 10 is a love letter to exactly that principle. Let me make the case for splitting a 6-digit code into 6 separate input boxes. You want each digit visually distinct. You want the user to see exactly where they are in the sequence. You want to prevent typos by constraining each field to a single character. It sounds reasonable. It sounds like good UX. It is in fact a masterclass in how to break the web. A developer in Switzerland spent hours trying to register for a GOV, the federal login system that 1.6 million Swiss residents now depend on for taxes, unemployment insurance, citizenship applications. The verification code form. 6 little boxes, 1 digit each. Refused to work. Not in Firefox, not in Chrome, not in Safari, not on Linux, not on Mac OS. 6 browser and OS combinations, all broken identically. The culprit? The boxes expected digit keys from the main keyboard row, but the developer was typing on a French AZERTY layout, where digits require holding Shift. The JavaScript handling key events was checking for raw key codes instead of the actual character produced. A native HTML input element would have handled this automatically. The platform solved this problem decades ago. One comment nails it perfectly. Web Developer Classic. Used JavaScript to replace a native, working, internationally supported input with a custom mechanism that doesn't work. And here's the part that deserves real attention. When the form broke, there was no way to report it. The support contact form requires the same verification code. The feedback system requires an existing account. The postal address leads to the federal chancellery, not the developers. A government system that locks you out has no side door. This is what happens when critical public infrastructure runs on closed, unauditable code. Nobody outside the development team can inspect the input handler. Nobody can submit a patch. The author had to reverse engineer minified JavaScript to diagnose a bug that affects every resident using a non-QWERTY keyboard. The fix is one line of code. The lesson is architectural. Public systems should be public code. This has been your daily tech feed for Hacker News for July 14th, 2026. This podcast is entirely AI-generated. Scripts by Claude Sonnet 4.7. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go open something that deserves to be shared. We'll see you back here tomorrow.